Well, hello, everybody. I am Jim Riggins with the Southeast Colorado Renewable Energy Society. Today, we're going to talk about the basics of renewable energy. This is normally a 45-minute to an hour class that we're going to try to complete in about 25 minutes. But I would still encourage any of you kids to type in your questions in the chat box as we go along, and we'll try to answer those at the end. Um, Let's start with the very basic question of what is renewable energy? What do we mean when we talk about renewable energy? There's three basic parts of the definition. The energy is naturally occurring. There is not a limit to the source, so it's an endless supply of energy. And most importantly, to compare it to fossil fuels, renewable energy is not carbon based. And we contrast that with fossil fuels that most of you may be familiar with: coal, oil, natural gas. And to differentiate these from renewable energy, these are non-replaceable in the lifespan of humankind. It takes millions of years for these to be created in the ground. They require extraction from the ground, either mining or drilling, and they are carbon based, so that when they are burned to extract the energy from these materials, they are releasing carbon into the atmosphere, and that creates some problems that we're going to talk about here in just a couple of slides. Now, when we compare fossil fuels and renewable energy, we have some advantages and disadvantages for each. Now, let's talk about fossil fuels first. Key advantages of fossil fuels are the infrastructure is established. And what I mean by that is that the pipelines have already been built to move gas and oil. The refineries are built to refine oil into its different products. The train tracks are in place to move coal from the mines to power plants. So the infrastructure built over the last 100+ years is in place and well established. And another key advantage is that they provide continuous power. As long as the plants are not being brought down for maintenance, you can burn coal, let's say, 24 hours a day to generate electricity, or burn oil. So you get continuous power from fossil fuels. Some very significant disadvantages, though, and that is damage to health, environment, and climate that's caused by not just the burning of these products, but also the mining and extraction of these products. And also today, another key disadvantage is that the energy from these products comes at a higher overall cost than that of renewable energy. So looking at renewable energy, the advantages are lower cost. The cost of fuel is free, which means that the price of energy can be very predictable over tens of years once you remove the cost of fuel from the equation. The renewable energy is much cleaner, healthier, and if it is replacing the burning of fossil fuels, it can slow or reverse the damage due to global climate change. But the disadvantage is that these fuels are non-continuous without some type of storage. The wind doesn't always blow. The sun goes down at night. And so without some type of energy storage system, you cannot have continuous power to replace 100% of fossil fuels. And in a lot of cases, new infrastructure is needed, particularly in rural areas where wind farms are being built. Transmission lines need to go in to get that energy to where it's needed. In the interest of time, I won't go through each of these categories, but let me just say, as we talk about the health, climate, and environment damage caused by the burning of fossil fuels, one landmark study in 2011 from Harvard Medical School looked at the combined damage from the mining, moving, and burning of coal. So not just the burning of coal, but actually the energy and the pollution caused by mining and by washing the coal, moving it to the power plants, burning it, and then removing the toxic ash to store that somewhere. And the total cost was $344 billion per year just in the United States for this damage to climate, health, and environment. Now, when we talk about renewable energy, when I do this in a classroom, I always ask for a show of hands and ask, what are the forms of renewable energy? And the only two answers I ever usually get are solar and wind. But you may find it interesting that there are actually 5 major categories of renewable energy. We're going to hold off on solar and wind because we're going to go into those in a little more detail in following slides. But let me talk about the other 3 categories. One is biomass, and biomass is energy that comes from plant-based material, grasses, algae, trees. And a couple of ways that you can extract energy from biomass is one to burn it in similar to burning coal, but you're now burning plant-based material to generate steam to drive a turbine to generate electricity. In Colorado, this is done in a lot of areas with the pine trees killed by the pine bark beetle and chopped up and burned for fuel. You can also take grasses and distill them for alcohol to be used as fuel. Another fascinating and fairly new source of biomass energy is algae, in other words, pond scum. And particular types of algae that are extracting energy from the sun and grow extremely quickly and reproduce extremely quickly, but have a very high oil content that can be extracted to make a form of natural-based diesel fuel to replace petroleum-based diesel fuel that uses oil drilled from the ground. Moving down to geothermal, down here in the lower left corner. Geo meaning earth, thermal meaning temperature or heat. So this is extracting heat from the ground to create steam to drive turbines to generate electricity. One of the countries that is using this to a very large degree because of how close they are to fault line and volcanic activity near the surface of the ground is in Iceland. Iceland produces more than 25% of their total electrical energy from geothermal plants. Water. Let's move up to water here. When I ask how do we extract energy from water, the most common answer I get is hydroelectric plants. A dam built on a river that creates a reservoir, which creates a huge amount of potential energy as the water stacks up behind the dam. That water can then run down through pipes using gravitational force to spin turbines at very high speed to generate electricity. 2 other up-and-coming sources of energy from water that are really fascinating. One is the use of tides. You can see these propellers underneath the water as the tides move in and out of bays and harbors. Those propellers spin, and whether they're spinning forward or reverse, they are generating electricity in both directions. There are about 8 large operational stations that are using tidal power today that range between 1.2 and 254 megawatts. And by the way, a megawatt is 1 million watts of power. The largest of these tidal plants is in South Korea at Siwa Lake, where they have an 18-foot difference between high and low tide. So an enormous amount of potential energy as the tides move in and out. You can also use the constant linear motion of waves to generate electricity. And these generators convert the linear motion, vertical motion of waves into circular motion to drive a turbine, which generates electricity. So 3 of the 5 categories of renewable energy. Let's take a deeper dive into solar and wind. You all may be most familiar with solar photovoltaic or PV panels that take the sun's rays and directly create electricity. You see these on the roofs of homes and in the large field out by the Air Force Academy. But there's other ways to generate energy from the sun. This is, in the upper left is a photo of the Ivanpah solar thermal facility. And this particular facility, the array that you see on the ground here, huge area, large number of acres. These are not photovoltaic panels. These are actually mirrors that are on trackers, motorized trackers that move with the sun and keep the sun's rays focused on the top of this tower. This tower is not painted white. It is white hot because it reaches temperatures of 1,022 degrees Fahrenheit. And what that does is it heats either a salt-based material or oil to very high temperatures. And then that flows down to a generator where it converts water to steam, and that steam drives a turbine. What's really neat about this is that the storage facility for the high temperature salt or oils can retain the heat overnight. So this plant can actually run 24 hours a day, even after the sun goes down. Solar hot water, or solar thermal. This is running pipes of water through these boxes, which are like mini greenhouses. The sun heats the water in those pipes, and then that heat can be transferred to what we call the domestic hot water, the water that you use for washing, dishwashing, clothes washing, bathing, and so on. And then finally, a very simple device is just a solar hot air. These boxes, again, a glass-covered box. Sun comes through the glass, heats the air inside. The glass traps the heat inside, and when the temperature inside the box is more than inside the house or the building, a motorized fan turns on and it moves that hot air into the house. So it's just a way to heat a building directly from the sun. Let's take a closer look, though, at the solar photovoltaic. So how does this work? One of the most common elements on the face of the earth is silicon, which is beach sand used to make glass. And it's a very stable material in terms at the atomic level. But if you do some fancy things to it, if you put a little bit of phosphorus in the silicon, the phosphorus has excess electrons in its outer bands, and it creates what's called an N-type or a negative silicon because it has a slightly negative charge. If you add a little bit of boron to silicon, it has excess electron gaps, and it draws electrons away from the silicon and makes a net positive or P-type silicon. And if you sandwich both of these together, nothing happens until you shine light on it. And then the energy from the light, from the photons, excites the atoms enough to where the electrons can jump across the boundary. And if you connect the N-type silicon to the P through a circuit, you will get the flow of electrons, which is electricity. However, that electricity that comes from a solar panel is what we call direct current. If you look down at this chart over here, which is voltage on the y-axis versus time, the voltage stays absolutely constant over time. This is called direct current. However, the appliances that you use in your house, the electricity you get from the power company, is what's called AC, or alternating current. It moves between positive and negative at 60 cycles per second in a nice sine wave. So you cannot plug your appliances directly into the power that's coming out of the solar panels. So what do you have to do? You have to convert that DC waveform to an AC waveform, and the device that does that is called an inverter, a solar inverter. So let's take a look at a typical house powered by solar. The DC power coming out of those solar panels comes down to the inverter. It's converted to AC power. If your house needs that power because of appliances being run, it goes into your circuit breaker box, and then it is used by any of your appliances and lighting that are drawing electricity. If, however, you're making more electricity than you're using in the house, it will go through a two-directional meter and actually drive your electric meter backwards and be fed back to the power grid so that your neighbors can use it, and also offset your electric bill by what you're giving back to the power company. Moving to wind turbines. Wind turbines look big and complicated, but they operate on a very basic, simple electromagnetic theory. And that is that an electric current moving through a wire creates a magnetic field. And the reverse is also true. A changing magnetic field around a conducting wire will generate an electric current. Excuse me. So what that means is that an electric motor and a generator are exactly the same device, just running in reverse of each other. If I wrap coils of wire around a shaft or an axle surrounded by high-strength fixed magnets, if I run an electric current through that copper coil, it will spin the axle and it acts like a motor. However, if I attach a propeller or turbine blades to that axle and the wind is spinning that copper wire through the magnetic field, it's going to generate an electric current, and that is how a wind turbine works, with some additional mechanical features to slow them down or stop them in very high winds so that they don't get damaged. So the basics of a wind turbine. Now, we talked about how renewable energy, which is non-continuous, can be helped by energy storage. Here is a list of some of the ways that you can do that. And this is a fascinating field for those of you boys and girls that want to get into engineering, is how to optimize energy storage for renewable energy. Let's just take a look at some of these options. Electrochemical means by using batteries, battery storage. You store the excess energy when you have it, and then when the sun goes down, the wind stops blowing, you draw from the batteries. Inside these little containment facilities here are gigantic flywheels, or like gyroscopes that are connected to motors. When you have excess energy, you spin these up, and these weigh thousands of pounds inside. You spin them up, and when you need the energy, you let those spinning flywheels run the motor backwards as a generator, and you draw the electricity from them. gigantic capacitors using electronic means to store on two conductive plates. You can compress air when you have excess energy, and use that compressed air to drive a turbine and a generator to create electricity when you need it. Pumped hydro is a technique that Colorado Springs Utilities uses because of the large altitude change between the mountains and the city. When you have the excess energy, you use pumps to move water to a higher altitude or higher elevation reservoir. When you want that energy back, you open up the valves, the water will flow down by gravity, drive a generator, and generate electricity. And finally, another category is to break down the water molecules through electrolysis, H2O, into its components of hydrogen and oxygen with your excess energy, and then recombine that hydrogen with oxygen from the atmosphere in what's called a fuel cell, which generates electricity and has as a byproduct only water. Okay, we still have 4 minutes left. This is actually our last slide. So how does all of this come together, let's say, in a house? So this actually happens to be my house, which is a net zero energy design that I put together, which means that all of the energy that we consume in this all-electric house, we produce on site. You can see 20 solar photovoltaic panels to supply electricity for all of our appliances and well pump and 2 electric vehicles. This is the south face of the house. We heat it completely with passive solar, just the heat of the sun coming through triple pane windows. These 3 devices over here are solar hot water collectors. Generates 100% of the hot water for our family of 4 that we use in the house. And because the house is super insulated and almost airtight, we have a ventilation system, and the input to that ventilation system comes through what's called an earth tube. It's just an open tube that's buried 10 feet below the ground where the earth is 52 degrees, so that the air is preheated. The clean, fresh air from outside is preheated underground before it is brought into the house. And that is a very quick look at renewable energy. And we're going to come back to see if there are any questions. And we have no questions. So I want to thank you all very much, and I hope you enjoy the rest of your Cool Science Festival. Thank you.